Hello everyone, welcome to this channel ML Guru. My name is Arjun Pukale. In this video we will see the concept of bias and variance. So let us consider a function, let's say sin x, which is nothing but the true relation between y and x. Now we will run an experiment. In this experiment we will loop uh, multiple times, and each time what we do is we randomly sample n points from this function and then fit our regression model on the sampled n points. So first what we do is we fit a simple model, meaning a degree 1 model or a linear regression model. So in this animation you see multiple such linear regression models, which is shown in this red color. Now these different predictions are nothing but the different output of the model given by this experiment, because we have run this experiment for many number of times, and this different predictions shows a particular output for different randomly sampled endpoints from this true function. Now let us do the same experiment with a complex model of degree 5. So this is a polynomial regression model, and every time we sample endpoints from this true function and fit this degree 5 model, and we get these different predictions which are shown in red color. Now let's make some observations on these two models. The first observation which we see is, in this simple model case, we see that all these predictions or all these models are close to each other. On the other hand, if you see here, all these different predictions are far away from each other, or in other words, different from each other. The second point to note here is, in this first case, if you take the average of all these predicted models, all these different models, you will see that average model is far away from the true function. On the other hand, if you see here, if I take the average of all these different red predictions, then you can notice that the average of all these predictions is close to the true function, and this is nothing but we call bias and variance. So the first, a simple model, is of high bias and low variance, and on the other hand this complex model is of type low bias and high variance. Now we will see in detail what is this bias and variance. So to make it simple, what I have done is I have simultaneously plotted all my predictions on both the experiments. So in this case, all these red straight lines are my different predictions made on different randomly sampled endpoints, and the same thing on the right side, which is a degree 5 model. So what do you mean by bias? So bias in simple terms is the difference between average of all these predicted models and the true function. So to make it simple, I have also plotted the average of all these models. So the green line which you see here is the average of these different predictions. So in the first case, you can see that this green line or the average is far away from this true function. So the bias is high because the difference between the average of all these predicted models and true function is high. So here we have a high bias. On the other side, you can see that this average model or the green line is close to the true function, which is shown by this blue line. So in this case, the difference between the two is small. So we have low bias in this case. Now let's see what do you mean by variance. So variance is nothing but, on an average, how the predicted models are far from the average of all the predicted models. So in other case, in other words, you can think of it as uh, how far are all these predicted models. So in the first case, you see that the red lines are close to each other, so we have low variance. On the right side we see that all these models are different from each other or far away from each other, so I have a high variance here. And if you look from the average model point of view, you can see that this green line is close from all this is close to all these red lines, and on the right side you see that this green line is different from all these red lines, so you can get the intuition of variance. Now we have two terms, bias and variance, and each of the terms can be high or low. So we have total of 4 combinations of bias and variance. The two models we have seen so far is the high bias and low variance model and the high variance and low bias model. So uh, these contours are nothing but the contour of the loss function, and this red point here is the optimal solution, and these different points are nothing but uh, the different models which I have predicted. So when my bias is high, you can see that the average of all these points is far away from the true function, whereas if my bias is low, the average of all these points is close to the optimal solution. Now let's look at variance. If I have low variance, you can see that all these points are close to each other. On the other hand, when we have high variance, then we can see that all these points are far away from each other. So we have seen two cases, which was high bias and low variance, which resulted in underfitting. This is nothing but the single degree equation. Now the next one is high variance and low bias, which is this point, which leads to overfitting or a highly complex model, which we had seen in previous example, which was of degree 5. But the ideal model which we want is the one which has low bias and low variance, which is this one, because in this you can see that the average of all these points is close to the optimal point, and also all these different predictions are close to each other. Now let's see how to select ideal degree for our regression model. So for that, what we have to do is we have to divide our entire dataset into training and validation part. This validation part is sometimes also called as testing part, but ideally it should be called as validation data. So let's understand underfitting and overfitting. So when you have underfitting, this means that your model performs poor on both your training data as well as this validation data. And to be clear, the training data is the one on which the model is fitted or model is trained on this training data only. You can divide your data set in a proportion like 70-30 or 80-20. So your model is trained on just on this training data and validated on this validation data. Now let's move to overfitting. When you have overfitting problem, this means that your model performs good on your training data and poor on validation data. But when you have ideal fit, it performs good on both the training data as well as the validation data. Now to select the ideal degree for our model, what you have to do is you must having a variety of options for choosing your degree of your model. Now in our case, the degree denotes the complexity of our model. The more the degrees, the higher is the complexity of our model. So on x-axis we have our model complexity. In this case we have degree, and on y-axis we have our loss, which is nothing but the mean squared error loss. So we try different values of degree, right from 1 degree, 2 degree, and so on. Now if we look at this graph, we have two curves. The first curve here is the training loss, which is plotted for this training data. This is the loss calculated for the training data after I have fitted the model on a particular degree. And the second curve is my validation loss, which is the mean squared error for this validation loss. Now if you see here, when you have a low complexity model, which means your model is underfitting, in that case, as you can see here, the loss is high on both validation as well as training. As I have said here, it performs poor on both training and validation data. On the other end, when you have a highly complex model, you know that it performs good on your training data. As a result, the loss is very low over here, and it performs poor on validation data. As a result, the loss is high over here. Now, if I want to show this graphically, you can see here that when you have underfitting, this example we have done in polynomial regression when we were implementing it in Python. We had seen that when we fitted the degree 1 or the linear regression model on this data, it did not perform very good on both the training data as well as validation data. On the other end, when we fitted a higher degree model, we saw that it works perfectly for our training data. As you can see, it goes through all the training points, but it performs poor on this test data. So this is overfitting. And we saw that when we fitted a 2-degree equation or a quadratic model, it performs good on training data as well as on the validation data. So how you choose your degree? So you can notice, as you increase the complexity, your training loss goes down continuously. But as you can see, the validation data initially goes down, but after some point, it again goes up. So this denotes overfitting, that your model has started to overfit. So you have to stop before your validation loss goes up. So this point is your ideal point, or this degree over here on the x-axis is your ideal degree. On the other hand, if you want to observe the accuracy instead of the loss, then you can plot a similar graph, but in this case the graph is somewhat different. On the x-axis you have the model complexity or degree in this case, as we had seen in the loss case, but on the y-axis, instead of loss, now you have your accuracy. Now in our regression task, this accuracy may be your R2 score, which we had seen while doing the implementation on in Python. Then when you plot your graph, you can see that when your complexity is low, the accuracy is low on both the training as well as validation data. But on the other hand, when it is overfitting, then your training accuracy is high but your validation accuracy is low. And again, your sweet spot is somewhere around here. It is just before the accuracy of your validation data starts dropping. So that's it in this lecture. Hope you have understood the concept of bias and variance and how to choose the degree of your model. Thank you.